Okay, this is video 1 for the angular momentum unit notes. For this unit, I want you to be able to calculate the angular momentum of an object. I want you to be able to solve problems using conservation of angular momentum. And finally, I want you to solve problems involving orbit. And I think you'll find that this unit is very similar to the linear momentum unit that we did earlier. So, linear momentum of an object. Remember, it is the product of the mass of an object and its velocity vector. So, momentum was P equals m times v. Now, there is this correlation between translational and rotational. Um, so, for angular momentum, we represent it with an L. And what this is, well, the rotational equivalent for mass is moment of inertia. And the rotational equivalent of velocity is angular velocity, omega. So there we have it. This is our formula for angular momentum. L equals I times omega. So this is a very simple formula, just like linear momentum. Now, something with this. This formula is only for a rigid body. So this formula only works when we have something like a disc or a ring, something that's not going to stretch when it's being rotated. So this will not work for pizza dough. Okay, another way of looking at this, just playing around with this formula now, remember that V equals R times omega. That's our bridge between linear and rotational. So omega would equal V over R. So we can replace that. We can say L equals I times V over R. Also, remember that moment of inertia oftentimes is some fraction times mr squared. So we can substitute mr squared for I. And this gives us a formula that looks like this. And notice in there that we have an m times a v. So what this leaves us with then is that angular momentum equals linear momentum times a lever arm distance, or a radius. And that should look very familiar. Remember that torque is a force times a lever arm distance. So again, just drawing up that relationship between linear and rotational. All right, we can also take a look at Newton's second law. Remember that Newton originally wrote his law as being delta P over delta T. Well, we can do the same thing for linear, or angular momentum. Instead of a force, we have a torque, and that equals delta L over delta T. Or I can say the change in angular momentum equals a torque multiplied by a time interval. So looking at this, this is another version of the impulse momentum theorem. So it's a very interesting relationship here. Okay, conservation of angular momentum. Remember that when it came to linear momentum, the initial momentum of all objects in the system has to equal the final momentum of all objects in a system. Well, we can do the same thing for angular momentum. So momentum is conserved whether or not it's linear or rotational. This conservation of momentum then helps us explain why rotating bodies will accelerate when we change the placement of their masses. So think of an ice skater. As she tucks her arms in during a spin, her angular velocity increases. So she experiences an angular acceleration. So this would be due to her changing her moment of inertia. She's changing the placement of her mass. All right, let's take a look at a couple examples here. Okay, this first one is for Halley's Comet. Halley's Comet has a period of 75 to 76 years. So that means it goes past the Earth or goes around the Sun every 75 to 76 years. That's actually a short-term comet. Halley's Comet follows an elliptical orbit. So if this right here is the Sun, Halley's Comet then follows a path that looks like this. At its closest position, Halley's Comet is 0.6 AU. Now, AU is for astronomical unit. And the astronomical unit then is roughly the distance from the Earth to the Sun. 1 astronomical unit, and hold on to your hats, this is pretty large, 1.496 times 10 to the 11th meters. It is a huge value. So at its closest, Halley's Comet is 0.6 astronomical units from the Sun. Its furthest, all the way out here, is 35 astronomical units. That's about close to Pluto out there. So it goes from Mercury to Pluto. When it's closest to the Sun, it's traveling at a linear velocity of 70.56 kilometers per second. And what we want to do is we want to find, so let's say that's a B naught there. We want to find its final velocity when it's farthest away from the Sun. All right, so let's take a look at this. We only have one object in the system here. It's Halley's Comet. So we have the initial angular momentum needs to equal the final angular momentum. So that means that the moment of inertia initially times the initial angular speed needs to equal the final moment of inertia and the final angular speed. Okay, so don't forget that V equals R times omega, so omega would equal V divided by R. All right, so what that means then is, and I'll use a capital R here. So that means then we're left with this. I initial equals V naught over R equals I final V over R. Now, Halley's Comet, we can consider that as a point mass going around. So for a point mass, the moment of inertia is mr squared. Now, something I noticed, the values for R change. So I need to have an initial value, R naught, right here and right here. Okay, we can do some algebra with this. The mass of the comet cancels. We get some cancellations here. So what we're left with then is that right there. So the final speed of Halley's Comet when it's the farthest point away from the Sun would equal that. Now, we could convert our astronomical units into meters. If you want to, go ahead, but I'm not going to. We just have that the astronomical units cancel out. So the velocity then would equal 1.21 kilometers per second. So when it's closest to the Sun, it's traveling over 70 kilometers per second. And when it's at its farthest point, it's only traveling at like 1 kilometer per second. All right, let's take a look at another example. This is a playground with a merry-go-round on it. The merry-go-round is spinning with negligible friction. A child is moving from the center out to the rim of the merry-go-round as it spins, and that's very hard to do, but let's say the child has a handrail to help. So the system then is the merry-go-round plus the child. The merry-go-round then has a radius of 1.3 meters, mass of 100 kilograms. The child has a mass of 30 kilograms, and the merry-go-round is initially turning at 1 revolution per minute. What will its rotational speed be when the child reaches the rim? Now, hopefully you can recognize that our answer should be less than 1 because the mass is moving closer to the rim of the merry-go-round. So that means that as the mass moves outward, the moment of inertia increases for the system, so the angular speed must decrease. So let's get a drawing here. So here's our merry-go-round, and we have a child that's going to start here and march their way out to the end as it turns. And this merry-go-round has a radius r. So what I'm going to do, I'm going to say m1 is the mass of the child, m2 equals the mass of the merry-go-round, the radius, and we have an initial angular speed of 1 revolution per minute. Now I do need to convert that revolution per minute into radians per second. So I would have 1 minute, 60 seconds, and 1 revolution is 2 pi radians. So that gives me an initial angular speed of 0.1047 radians per second. Okay, so we have 2 objects in our system, the child and the merry-go-round. So we can use our conservation of angular momentum. All right, so angular momentum is I times omega. Now I'm using, just because the child and the merry-go-round are connected, they have the same initial angular speed. Likewise, they'll have the same final speed. Okay, so the child is a point mass. So the child's moment of inertia then would be m r squared initial. The merry-go-round is a solid disk, so it's 1/2 mr squared. And I can go ahead and get rid of this little naught symbol because the radius of the merry-go-round is not going to change. There we go. Now the child starts out at the center of the merry-go-round, so that's r equals 0. So this whole term goes to 0. All right, so what we're left with then and I can factor some stuff out on this side. All right, and it looks like I can also cancel out the radius of the merry-go-round. All right, so finishing up our algebra then. There we go. And I can go ahead and plug in my values. So we get 0.065 radians per second. That doesn't tell me a whole lot. Maybe I want that back into revolutions per minute, so I can convert that back. So we see that the merry-go-round will go from 1 revolution per minute down to 0.62 revolutions per minute from the act of the child moving from the center out to the rim. All right, well that finishes video 1.